in our next section with BGP, we're going to look at the specifics of doing iBGP peerings, some of the different design choices that we can use, either having a full mesh of peerings, using route reflection, or using confederation. Now again, the key design point to keep in mind here with iBGP is that by default, anytime we learn a route from an iBGP neighbor, we will not advertise it onto another iBGP neighbor. So the default implication of this means that there has to be a full mesh of peerings between all of the devices. Now, as I mentioned previously, this would give the routers the most diverse view of the BGP topology, and then have them able to choose whatever particular path that they want to out of the network, but it's going to be at the sacrifice of the amount of overhead in the control plane. So if we're looking at this from the perspective of the global BGP table, for every eBGP peer that we have, there's going to be somewhere around 300,000 to 400,000 routes. Then if we are peering with every single device internal to our network, means that we have to send those 300,000 to 400,000 update messages out to each of those peers. So it will give us the most options for the path selection, but again, it's going to be at the sacrifice of the amount of control plane overhead. So in our next example, we're going to look at all of the devices inside of the internal network here, inside the same autonomous system, where this AS is going to be 100. So first I'm going to establish the eBGP peerings from router 4 and 6 to AS 54, then from router 2 to AS 254. So those are going to be the external peerings where we are learning routes from outside of our autonomous system. Then our ultimate goal is to take these routes and pass them to the internal neighbors. So first let's start on router 4 and router 6, who are on the network edge. And from router 4's perspective, we should be establishing a peering with the address 204.12.28.254, which is BB3's address. Now before we even do this, we could do a basic low-level connectivity test in BGP to figure out if we have transport to that address and whether or not that remote neighbor is going to accept the BGP peer from them. The way we can do this is to try a telnet going to the particular address using port 179. Now we can see on router 4 we did get an open message back from the telnet, which essentially means that just at a basic layer 4 point of view, this remote neighbor is listening for a BGP session to come in from router 4. Now if the remote neighbor is not configured with the peering session on the way back, then we would see that the connection is simply going to be refused. So for example, on router 4, if I were to telnet to, let's say, router 6's loopback at port 179, I could telnet to router 6's loopback on its own. So this tells me I do have basic connectivity. But if I were to try to do this at 179, the connection is refused because when I send the SYN packet to 6, 6 is not running the BGP process yet with router 4, so it replies with a reset. So as we can tell, where the first telnet to the remote neighbor opens, the second telnet to router 6 is denied. It means that this particular neighbor is configured with a BGP session back to us. So if for some reason we're having problems establishing the session, that would be a good layer 4 test to see of whether just the BGP process is configured and we don't have any type of layer 2 or layer 3 filtering issues in the network. So next, let's actually configure the BGP process. This is router BGP 100 on router 4. And we'll peer with 204.12.28.254. Their AS number is 54. Now these values, this is not something that we could guess in the topology. We'd have to be provided with whatever the address is that we're trying to peer with and whatever the autonomous system number that they have configured is. Likewise on router 6, if we look at the show IP route connected, our link to BB1 is 54.28.1 and their address is .254. So on router 6 we'll configure BGP 100 and we have the neighbor 5428.1.254 there in AS 100. On router 2's connection, actually no, they're not in 100, they are in 54. So we see the notification message there. That means that I've configured the wrong autonomous system number. So they should be in 54. And we should see the BGP peering come up here. Which we have. Now on router 2, its connection is going to be to 192.10.28.254, which we do have connectivity to. But in this particular design, BB2 is configured to peer with router 2 using AS number 200. So under most of our examples, you would see that whoever is attached to BB2 actually would have the BGP process configured as 200, because this is what the neighbor statement is pre-configured on the backbone router. Now, there can be certain designs where the BGP neighbors do not agree on the AS numbers, and it's still correct to have that. Typically, in a real-world design, it's when you're doing an AS migration from an old autonomous system number to a new autonomous system number. And this is what, under the BGP process, the neighbor, so they are going to be in remote AS 254. Then our command to change our local autonomous system. This is when we send the BGP open message. This is the value that we're going to use in that particular communication. So normally the local autonomous system number is going to come from whatever we have configured globally. But in the case where the global AS number doesn't agree with what that particular neighbor is listening for, we can use a different value for the local AS. Now, if you look at the specific options on this command, there's some other features for the configuration. Depending on the version, the no prepend here means that we will not add the AS number 200 as the routes are coming in from the neighbor. Then replace AS, dual AS, would allow us to support a configuration where BB2 is migrating its neighbor statement, where currently it's going to say neighbor, whatever router 2's address is, remote AS 200. But then in the future, it's going to update this command so it says that the remote AS is 100. That's what the dual AS support is for. So again, the design about this would be that AS 100 has just acquired AS 200. While all of the remote peers are waiting to update their configurations, we can do kind of a hack on the process that's a temporary band-aid for the configuration. That router 2 says, as I send my updates out to BB2, I'm going to tell them that I'm in AS 200. Now, if I know that sometime down the road they're going to update their configuration to point at 100, but I don't exactly know when, then router 2 with the dual AS support would be able to offer them whichever value that they want. So it essentially sends two separate open messages, one for AS 100 and one for AS 200. Then they're going to accept whichever one that they have configured on their side. So once we have this configured, if we look at the show IPBGP summary, we should ideally see that the peering comes up. Now from this output in show IPBGP summary, what we want to look at here is that there's some timer value that's associated with the neighbor, and the state here doesn't have either active or idle. It should be some numeric value. So any integer 0 or above, that's going to show us how many particular routes we are receiving from that neighbor. Where in this case it says that the neighbor is active, it means that there's something wrong in the peering. Now to figure this out, sometimes there'll be issues where you can't actually see from the debug. But if we look at router 2 and look at the debug IPBGP, let's see if we receive an open message in from backbone 2. Now again, this should be the correct address if we ping to that neighbor. Okay, we do have connectivity. Then let's look at the debug IP packet. But I'm going to look at this just for BGP traffic. So I'll say access list 100 permit TCP any equal to BGP any, and any equal to BGP. Because again, I need to account for either source port 179 or destination port 179. Then I'll say debug IP packet detail 100. Now I may not be able to see this particular output on router 2 what the problem is, but specifically in this case, BB2 is configured to accept an authenticated session from router 2. Where router 2 I haven't configured it with a password, so it's not going to be able to establish the session. We should see though, if I clear IP BGP, we should see router 2 trying to send the packets and then getting the session denied. Unless I'm not logging. No, I am logging to the console because it does show the output there. Let's try this. Let's say show run section router BGP. So it is the correct value here. Let's try this. Let me remove the BGP process. And then I'll reconfigure it. So BGP 100, I have that particular neighbor. So we should see router 2 send the packets out locally. But it's not generating them. So what this means is that, let's see, and this is on a connected link. The neighbor that's not doing the authentication, there's really nothing in the debug that's going to show us that. Now, if we did configure the authentication and the password was wrong, we will get a log message saying that the MD5 hash is incorrect. So if I say for this neighbor the password is ABC, we'll see that once we try to establish the session, we're going to get a log message back in saying that the MD5 digest is incorrect, which essentially just means that the password is wrong. So let's try clear IP BGP. And like I mentioned before, a lot of this is really slow to converge. So if there is a problem in the establishment, it may take a while to even figure out what the problem is to begin with. So let's let this debug run for a little bit, and let's move on to the other peerings. Now, what I'm going to do here is that without having to do route reflection or confederation, it means that we're going to need a full mesh of peerings in the topology. So configuration-wise, it means that each router would need 9 neighbor statements pointing to all of the other devices in the topology, which is feasible. It's not that bad to maintain just 10 peerings. But if there's 100 or 1,000 routers in the network, then a lot of times doing the full mesh is not going to be feasible. Now, one way I can simplify this is to take the IBGP peers and put them into a template of configuration that is called a peer group. So when I create the peer group, I'm going to apply different attributes onto it, like the remote AS number, the update source, and maybe if I'm doing some sort of route map filtering, I can apply that onto the peer group, then put the actual neighbor's address into the peer group, in which case they are going to inherit all of that configuration. Now, the peer group configuration will also be an optimization of the actual update state machine, because there is one update that is sent to the entire peer group, as opposed to individual updates that are sent to the neighbors. So it essentially means that if I have 10 neighbors in the peer group, the best path selection is only run once for all 10 of those neighbors, as opposed to run 10 separate times depending on their individual policies. So to do this, we'll start the BGP process, BGP 100. I'll specify a neighbor and give it a name. I'll say that this is my iBGP peers, and this is a peer group. The neighbor iBGP peers, everyone in it is going to be an AS100. The update source is going to be my loopback. So I'm assuming up to this point I already have connectivity between all of the loopbacks. Then I would need to specify for the actual neighbor addresses 150.28.2.2, it's part of the peer group iBGP peers. Then 3.3, 4.4, etc. for all of the addresses. So what makes it easier about this configuration now, not only is it an optimization behind the scenes of how the update process works, it makes it easier that I can just apply this template onto all of the routers. So now I could go to our Notepad configuration and simply say that I'm going to take this same type of template and then basically apply it to everyone. So I have peers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, depending on where I'm referencing this configuration from, one of the commands is going to get kicked out because it's not possible to peer with your own local address. So when I apply this configuration on router 1, it's going to tell me I can't peer with my own local address. Okay, which is fine because the parser is just going to ignore that command. But now I can take this template of config and basically apply it on everyone, and I should see the full mesh of peerings come up. So I'll do this just from the access server. I'll say send star, and then I have all 10 of these peerings. Now you can see the send command, it didn't read the entire buffer, so probably some of the commands were taken, but not all of them. So I need to cut down on a couple of these lines. I may need to send this in 2 separate groupings. Let's do this. So first we'll send the peer group config. Then the second portion that is the neighbor statements. So essentially this would be the same as going to each of the consoles and just pasting this in, but doing it from the access server is going to save a little bit of time here. So now if we were to look at router 1, we can see it did take all of that configuration, but it said for my local loopback, I can't configure myself as a neighbor, which is fine, like I said, because the parser is just going to ignore that command. So now from everyone else, if we look at the show IPBGP summary, we should see that all of the peers are up and that we are learning routes from the border routers, which in this case are router 4 and router 6. Now router 2's configuration, it's still not showing me this debug message, so let's just change it to the correct config. Okay, it should be that this neighbor is using the password Cisco. I would be able to go to the other side on BB2 and see the error message. The problem with this, though, in the lab exam, you're not going to be able to see what goes on in the backbone routers. So if we actually look at, let's go to BB2. And look at what its configuration actually reads. So under BGP, there is the peer group configured. It says that those neighbors are in AS200, the password is supposed to be Cisco, and then these are the individual addresses. and my AS number is 254. Again, the problem with this, there's no way to really infer what this configuration is without actually looking at it on the other side. Now on RREX, if you're practicing these exercises later, you can go to the Access server and log into to BB1, BB2, and BB3. Then you'll see you can run different show commands like show IP BGP. But in the actual exam, you're not going to be able to do that. So ideally, you would want to stay away from these verifications, but as kind of a last-ditch effort, if you can't figure out what's going on, then you can use the backbones for some of these basic checks. Okay, so now let's look at the rest of our network. So we essentially have a full mesh of peerings inside AS100, plus the peerings that are going to the eBGP neighbors. So as the result of this, what we should see is that for every peer that is talking to router 6, we should see that the eBGP update that came in was then passed along to these iBGP neighbors. However, once the iBGP neighbors receive them, so for example, when the update goes from BB1 to router 6, 6 sends it to router 5, 5 is not going to send this back to any of its peers, because the normal behavior is that you filter out those updates between the iBGP neighbors. So without route reflection, you cannot exchange any iBGP learned routes to other iBGP neighbors. So if I were to go to router 5 and look at the show IPBGP summary, if the network is configured correctly, the only neighbors I should be receiving updates from should be routers 2, 4, and 6, because these are the edge routers that are learning their prefixes from eBGP. Which is what I do see. So we have router 2, we're learning 3 routes. Routers 4 and 6, we're learning 10 routes, because both of these are coming from the same remote autonomous system. Now, if we look at the actual result of this from the show IP BGP, this is going to show us the actual table about what those particular prefixes are. Now, as a quick review on how to read this output, well, we're going from the left to the right. Between the asterisk and the lowercase I, okay, or it could be a null value there, depends on who we're learning the update from, we normally should be receiving or seeing the greater than sign, which means that the route is a best route. The best route is the one that is candidate to be installed in the routing table, and the one that we're going to advertise to our other peers. So it's essentially the winner of the best path selection. In this case, I don't see the greater than sign on any of these, so it's going to tell me there's some problem in the selection process. So we'll come back to this in a second when we look at the actual routes. Okay, next to where the greater than sign normally would be, this lowercase I, it means that it came from an internal BGP peer. So for any of the edge routers, like if I were to go to router 2 and show IPBGP, we see that some of these routes came from iBGP peers, some of them came from an external peer. Next, we have the actual prefix, where if the subnet mask doesn't show up here, where we see /24 and then nothing for these routes, it means that they have the classful mask. Whereas the prefixes 112, 113, 114, 115, etc., those are class A networks, so it means they have the mask of /8. Anything that is a subnet or an aggregate is going to show the actual mask value there, like these two /24s. Next, we have the next hop value. This is what we would need to know via IGP in order to actually use the prefix. Now, as we see for these particular next hop values, when router 2 is learning the routes from routers 4 and 6, these values have not been modified. So when router 6 is receiving the update in from BB1, BB1 says the next hop value is whatever you're peering with here. When router 6 sends this down to 2, the next hop value is not changed. This would then mean router 2 needs a route to get to this next hop in order to actually use the route. We'll also see this is one of the first prerequisites of running the best path selection process. If for some reason I don't actually have a route to the next hop value, then the route is not valid and I cannot actually use it. Next field would be the multi-exit discriminator, which is a non-transitive attribute. So it's going to be only locally significant between me and my directly connected AS. The local preference is 100 by default. The weight value is 0 for anything that's not locally originated. Then we have the AS path followed last by the origin code, where I for IGP is going to be better than $ for incomplete. So like we talked about before in redistribution, anytime we redistribute a route into BGP, it's going to get the origin code of incomplete. So this would be less preferred than a route that was originated with the network statement under the BGP process. Now there's a question, can we use the next step self command? This would be one of the possible design solutions for this. So we'll look at a couple different options on how to solve this issue. But on router 2, if we were to look at the show IP route output, or actually, let's say show IP route BGP to cut down on the output a little bit, we could see that router 2 is installing the prefixes learned from its eBGP neighbor, but not any of the prefixes learned from the iBGP neighbors. And the reason why is going to be that issue with the next hop reachability. Now, the way that we can specifically verify this is if we were to say show IPBGP followed by the longer prefix, let's say 118.0.0.0. We see in this output it says that there is no best path, which means it cannot be advertised to any peer. Specifically, the reason why there is no best path is that the next hop values are inaccessible. So on router 2, if I were to say show IP route 54.28.1.254, I don't have a route to that exit point. Likewise, I don't have a route to 204.12.28.254. So since I don't know how to get towards the next hop value, it means that if I were to try to install the route into the routing table, the route recursion process will ultimately fail, and I won't be able to switch the traffic out the correct interface. Because remember what we talked about before in the routing process. The goal of the layer 3 routing process is to figure out what is the outgoing interface. Once we figure that out, then we send the packet to the switching process to actually move it between the links. Then finally we go to the encapsulation where we're actually building the layer 2 header. But if the routing process doesn't know the outgoing interface, then the switching is going to fail, and then ultimately the encapsulation is going to fail. So in BGP we have this automatic check built in that says if you can't do route recursion, I'm not going to consider the route, because I know that I'm going to cause a traffic black hole for this destination if I actually install it or advertise it to other peers. Now, the solution to this design problem is pretty straightforward. The issue is that we're learning routes that we don't know how to get to the next hop for. So there's only two possible solutions for this. Either we give them the route to that next hop. So if router 2 actually knew how to get to the frame relay interface between router 6 and BB1, and knew how to get to the LAN interface between router 4 and BB3, then we wouldn't have this problem in the first place. The other option would be to change the next hop to something router 2 does have reachability to. Now, whether that be the actual address that we're peering with on router 6 and router 4, whether it be the interface address of the Ethernet of router 4 or 6, it doesn't really matter what it is. As long as it points us towards the correct exit point, and it's something we already have in the IGP table, that's really what the ultimate goal is here. So we could change the next hop by either using the next hop self command, or we could do this manually under the route map. As long as we address the problem somehow, that's really what the ultimate design goal is.